Hi everyone, this video we're going to go through differentiating y equals ln x, or y equals log base ex. We've done the derivative of y equals e to the x, so we're going to look at the method of how to get this one. So y equals log base ex, we convert that to an index statement, we get e to the power of y equals x. Now we're going to do something tricky here. We're going to differentiate this function here, x equals e to the y. It's a little bit tricky. So if we have y equals x squared, we'd say dy dx equals 2x. But here we've got x equals e to the y. So I'm going to say dx dy, the derivative of x with respect to y, is equal to e to the y, isn't it? So this function here, the derivative is just e to the power of y. Now this is another tricky thing. These things behave like fractions. So we want dy dx, not dx dy, so we're just going to flip it upside down. So dy dx is equal to 1 over e to the y. If we look at our original definition, e to the y is x. So we get that the derivative of ln x is 1 over x. Now this little proof is repeated on page 58 of the handout, if you want to have a look. Okay, the derivative of ln of x is 1 over x. Okay, now if we want to differentiate some functions that look a little bit trickier, using these logarithmic laws is really handy. So we know log xy is log x plus log y, log x over y is log x minus log y, and log x to the k is k log x. So those three there are really helpful. Okay, and sometimes it's basically the only way you can do the derivative is using these log laws. So let's have a look at a few of these. First of all, I think it's interesting that the derivatives of a certain log functions are all the same. So if we look at ln 3x, that's ln 3 plus ln x. So the derivative of ln 3 is just 0. The derivative of ln x is 1 over x. So that's just 1 over x. Ln x squared is just 2 ln x. So the derivative juice will be 2 times the derivative of ln x, which is 2 times 1 over x. And the last one, ln x over 2, is ln x minus ln 2. The derivative of ln 2 is 0, so we just get 1 over x. So look at a and c, they're the same derivative, different functions, but the slope is the same. So let's have a look at the graph of those. They're basically just translations of each other. So there's ln 3x, there's ln x, and there's ln x over 2. So they're just translations. So if we take any particular x value you like x equals 1, the slope is actually the same at each different x value. That explains why the derivatives are all the same. Okay, what about this one? ln 1 minus 2x. Okay, we're going to need some chain rule here. We can't simplify that. It's not ln 1 minus ln 2x. We can't simplify that any further. So let's kind of use the chain rule where we define a new variable. It's the long way. So y is now ln u, where u is 1 minus 2x. du dx is negative 2. And dy du is 1 over u. Now we want dy dx. So using the chain rule, dy dx is dy du times du dx. So it's 1 over 1 minus 2x times negative 2. Or negative 2 over 1 minus 2x. Now if we generalize this, you'll find that using the chain rule every time, you get 1 over whatever the function is here, and then using the chain rule, multiplied by the derivative of this function inside the brackets, which we normally call the inner function. Okay, so that is another really important rule. That is covered on page 59 in your handout. Okay, let's look at this one. Now, ln, oh gosh, this could be really tricky if we try and do it using that formula. 1 over everything in there times by the derivative of that, and to get the derivative of that, we're going to have to use the quotient rule. It's a bit of a nightmare, but if we know our log laws, we know that log a over b is log a minus log b, and that just makes life so much easier. Now when we do the derivative of ln 1 plus x is just 1 over 1 plus x. The derivative of ln 1 minus x is 1 over 1 minus x times minus 1. There we go. So there's the derivative there, and that could take a whole lot more effort if we didn't use those log laws at the start. Okay, great. So we've got some basic laws for doing derivatives, and there's the most important one highlighted there. Let's have a look now. So there's that really important rule down there. So for those functions, that's what the derivatives actually are. Let's have a look at a few more. I'm looking at C here on page 60. We've got y equals x cubed ln x. So if I define u as equaling x cubed and v as equaling ln x, we're obviously going to use the product rule here. So u dash is 3x squared, v dash is 1 over x, as we've just learnt, and then we just use the product rule, this kind of cross method. So the derivative is going to be u dash v, 3x squared times ln x, there it is there, plus v dash u, so 1 over x times x cubed. There we go there. So it simplifies to 3x squared ln x plus x squared. We can factorise out the the x squared, and we get that expression there for the derivative. So there's an example of using the product rule now. So we've done the chain rule, we've done the product rule. Of course, we can apply this to using when we're using quotients as well. Looking at page 61, this is part A. I'm just going to look at part A. Again, we could look at this one and get quite complicated. We say, okay, the derivative is 1 over x e to the minus x, which is true, times by the derivative of x e to the minus x, and then we'd have to use the product rule, u dash v plus v dash times u. That is actually the answer to that one there, and then I'll have to start simplifying, but there's an easier way of doing it, and you can see the answer on this page here. The easier way to do it is start by using your log rules right here. Log AB is log A plus log B. This then simplifies ln e to the minus x to minus x. Once we have this expression here, y equals ln x minus x, it's really easy to do the derivative. The derivative is 1 over x minus 1. So you can see using these log rules really important to use those when we're doing these differentiation of natural log functions.